Factorization-Aware Training of Transformers for Natural Language Understanding on the Edge, work presented at InterSpeech 2021. A growing number of users rely on voice-powered virtual assistants to do their daily activities. Virtual assistants typically rely on automatic speech recognition and natural language understanding to perform their function. The pipeline of these tasks can be performed either on the cloud or on the edge. Edge processing has the benefits of better privacy, faster response time, and robustness to poor connection. However, on-device resources are limited in terms of disk space, memory, CPU, and GPU. Therefore, models need to be compressed. Consider a typical model architecture for performing the three NLU tasks: domain classification, intent classification, and NER. In order to put this model on device, we need to compress this model. We first replace the backbone encoder with a smaller version. Then, looking at each transformer block and the components, we replace the dense layers with their factorized version. The whole factorized architecture with a per-specified lower rank factor is trained end-to-end using a joint multitask loss in a Factorization-Aware training setup. We present results on 3 datasets. We systematically experiment with lower rank factors to further compress the model. We show that in the naive factorization setup, the model performance degrades very quickly, and the model suffers from catastrophic forgetting. Whereas in the Factorization-Aware training setup, the model performance degradation is orders of magnitude slower, and therefore enables use of lower rank factors for compressing the model. We then ask which model components rely more on Factorization-Aware training to produce satisfactory results. We calculate Factorization Gap along the network depth. We show that for self-attention layers, as we move along the network depth, there is a downward trend in Factorization Gap, whereas for feed-forward networks, there is an upward trend, indicating that in deeper layers, feed-forward layers are more reliant on Factorization-Aware training to produce satisfactory results. We also studied the design space for inference time implementation of factorized models and asked, how can we trade off memory and computation? In this figure, we plot the peak memory consumed by the model versus the computation required for doing one forward pass along the network depth. We show that as lower rank factors are used to train the model, this trade-off gets exponentially better. For more details, please check out our